Hi everyone. So in this technical walkthrough, I'm just going to be going over how my project detects whether an audio clip is a cappella or not, and how each component of my repository contributes to that pipeline. So just as a general overview with my repo here, obviously I have my README, my setup, my attributions, which just kind of show what the project does and how to run it. Then I have my SRC file, which has the pre-processing code that converts raw audio into the MEL spectrogram features, which is really just important for me in order to represent it accurately for the machine learning component the um, of the pipeline. So then there's also the models, which are in here. So there's the logistic regression classifier and also the scalar, and they're pre-trained. So because you wouldn't have access to my data set because I made it myself and it's in my Google Drive, I decided just to put the models into my repo to make things easier. And then, yeah, on top of that, I have my two notebooks. The first one, which is the exploration, which is just the pipeline where I ran experiments. And then there's also the demo, which I used in my other video, and that is just very user friendly if you want to try your own audio clips as well. So without further ado, let's go into the SRC file and pre-processing, and we have our audio file here, which is just the core pipeline, where I took an audio file and then you can force it into a mono and then resample everything into 22,000 hertz so that different recordings are comparable. Then it converts the signal into a MEL spectrogram, which represents how energy is distributed across the human perceived frequency band over time, which I also showed in the demo. And then finally, I convert it into decibels and to a 2D matrix. It's kind of like an image that becomes the numerical input for all of my models. The next thing, obviously, is kind of just the model artifacts as well. As I said here are the two here, the logistic regression classifier and the scalar. I talked about those already, so I'm going to keep moving on. And so at this point, let's go into the notebook here, which is the exploration notebook. This is where I developed and validated the full pipeline. I loaded my labeled audio clips from Drive, as you can see here, and then I converted them into the MEL spectrogram features. I trained several classical models. I visualized them with the PCA, and then I also tested for the robustness with noise experiments as well at the end. So as I said, there's the data that I collected from my own recordings, and then I was able to kind of put them into the acapella and non-acapella folders, 17 of each. Here I decided to use a GPU even though I didn't need to, simply because if it was to be scaled up to a larger data set, this would be important for scale, whether it's the size of the number of recordings or the length of the recording itself. Yep. And then here is the split. X is the list of spectrograms and Y is the labeled vectors. And then let's keep going here. We have the spectrogram stuff that I did. And so for each spectrogram, which has a shape numbered of MEL bands by time, depends on the clip size as well. I decided to fix them and reorder them so that each clip became 128 dimensional vector. And this is just a simple handcrafted embedding that captures how energy is distributed across frequencies. So it made it easy to put that then into the machine learning, which I do right here. So this is the train and the test based on the logistic regression. And as you can see, there are both classes, and I balanced the split with 30% on the test and 70% on the training. From this, you can see that the numbers are quite small here, but the accuracy was very impressive at 100%. I also created a confusion matrix, as you can see here, which shows that all acapella and non-acapella clips are classified correctly, which just kind of told me that the feature space is linearly separable and that the problem is very learnable even with very simple models and a small data set. The next thing I did was kind of scaling and a stronger metrics, and also trying other like the random forest comparison as well. So I scaled the features to you know, zero mean and unit variance, which is kind of just standard practice for the linear models, and with an F1 score as well, as you can see here, and a confusion matrix, as you can see here. This comparison kind of just shows that that it was very high, but when you actually use the random forest, you can see that there is a much lower accuracy and test result. This kind of shows that the key strengths are that the spectrogram is based on feature engineering, and that a simple linear boundary is actually just a really good fit, and as opposed to complex trees that you'd have to do otherwise. Then I did some regularization work as well, and this was important because I wanted to make sure that the model was not overfitting. And as you can see with L1, it definitely decreased the results. And then furthermore, I decided to do some hyperparameter work as well, and you can see that even with huge differences in the size of the hyperparameters, I was still able to get 100% accuracy, as you can see in this graph here. The next thing that I did was a PCA visualization, where I was able to apply the PCA to the dimensional vectors into two principal components, and it kind of cluttered into two components here. As you can see, the red, which is acapella, was able to cluster very well together, while the non-acapella stuff was kind of more spread out, which makes sense as it's a bigger category with more variability. But it kind of shows how, especially here with the explained variance ratio, over 80% can be explained simply by the PCA, which was really cool to see. Great. Besides that, I also did some ablation work and showed the robustness by adding Gaussian noise and the features kind of just to simulate the if it was noisy, which can happen with audio files, especially if it's recording in a noisy area. And as you can see from down here, the results did get worse with an error analysis of 83%, which shows that there are some issues when you increase the amount of noise. And great, that's the majority of the work that I did and the exploration. The final thing I wanted to quickly talk about was the demo. Completely independent from the training pipeline, and it kind of simulates how an end user would interact with the system. It loads the data, the pre-trained model, of course, and then it also kind of asks the user to upload their own file that they want to have looked at, and then it applies the same pre-processing pipeline, the MEL spectrogram and the averaging to the uploaded clip. And then after doing all of that, it runs inference, and as you can see here, I already ran one, and it kind of outputs both the MEL spectrogram as well as the classification and how confident it is about that classification. And it's not always 100%, but oftentimes it is very, very high. So because I could easily share the code from the exploration file, and then I also have the models, it's very easy for anyone who wants to use it to use this as well. So great, let me go back to the overview here. And just to kind of summarize is I built an audio classification pipeline that detects whether a clip is a cappella or not using frequency-based features. It does not matter the length of the feature, how long it is able to do this classification very accurately, obviously within reason. And for future extensions, like I mentioned, for robustness, you can increase the amount of data that you're using, as well as maybe taking this and trying something new with other different types of classification, whether it's music or some other component as well. But this project just shows how lightweight classical models can solve really meaningful audio tasks with some feature engineering on the back end. So thank you so much for taking the time and listening to me talk and walk through my code with you.